Hey guys, how you doing? Hey, we are solving some more equations today. Today we're going to look at equations with variables on both sides. Even though it's not really anything different, it kind of throws people off sometimes, so I want to make sure that we touch on this as much as we can. So take notes just like you normally would in class. Pause it if I'm going too fast, or if you want to look at something again, you could rewind it. That's really the nice thing about having a video. Please email me or send me a message through Stream if you have a question. I will be online for the most part today, checking in on stuff. Okay, so this first slide just kind of gives you a summary of what's happening. It's talking about collecting terms and putting them on the same side. So we haven't seen variables on both sides, but today we will. And so all we have to do is make sure that we put the variables on one side and all the constants on another. One thing that is a helpful hint that your book and I talk about is that trying to keep the variable positive. If you can, that's great. If not, it doesn't matter. Okay? You still just divide by a negative, and I'll show you what I mean here with the example. So, going right into an example, we have 7n minus 2 equals 5n plus 6. So, what I'm going to do is bring my variable over to the left side. So, I chose to bring my 5n over because look what happens. When I subtract 5n on both sides, I'm left with a positive variable or a positive coefficient in front of the variable. So when I subtract 5n, I'm left with 2n minus 2 equals 6. Okay, now guess what? We have a two-step equation, something we're very used to seeing. So I want to bring this 2 over to the other side. I'm going to have to add 2 to both sides. Then I get 2n equals 8. Okay, final step is to isolate the variable, divide both sides by 2, and I get n equals 4. Okay, so it's pretty straightforward. It's just we're adding that variable in there, and like I said, it kind of causes issues sometimes with people for whatever reason. All right, let's look at another one. 4b plus 2 equals 3b. Okay, this time we don't have a choice. We have to bring our 4b over to the right side. No big deal. But when we subtract, oh, I see what they did here. They subtracted 3b. I probably wouldn't do that, give me an extra step, but actually watch what happens. So when we do that, we have 1b, or b, left over. B plus 2 equals 0. Then I'm going to subtract 2 on both sides, and I get b equals negative 2. You absolutely could do it that way. If you bring 4b over, it's the same amount of steps, so it's totally up to you. That's the beauty of this. Whatever you do to one side, as long as you do it to the other, you're not changing anything, right? And it'll work out. Okay, now we're going to pump it up a notch or two here with this. This problem has every single step in it. Okay, it has distribution. It has combining like terms. It has variables on both sides. So everything's in there. So we're just going to take it nice and slow, step by step. First thing we're going to do is distribute this negative 5 to the 7 and the negative 2a, or minus 2a. And when you do that, you bring everything else down. So you got 4 minus 6a plus 4a equals negative 1. Okay, and they're showing you here, this is negative 5 times 7 and a negative 5 times 2a. That's the distribution. When you fix up this distribution here, this negative 5 plus 7 is negative 35, or you can think of it as minus 35. It's the same thing. Negative 5 times negative 2 gives you a positive 10a. Okay, now we've distributed, so the next step is to combine like terms. So if I look on the left side of the equation, I have a negative 6a plus a 4a. Those are like terms. I'm combining those. Okay? And then when I look on the right side of the equation, I have a negative 1 minus 35. Those are also like terms. I'm going to be combining those. So this 4, nothing happens to it, so I'm dropping it down. Then I have negative 6 plus 4a. That will yield a negative 2a. All right, so we've taken care of the left side. Now, on the right side, we've got negative 1 minus 35. That gives me a negative 36. Then I'm dropping down my plus 10a. Okay, so now we've combined like terms. So now what we have to do is get our variables on one side, get our constants on the other. Doesn't really matter which one you do first. Okay, I'm going to take this 36 and I'm going to add 36 to both sides. So that gives me 40 minus 2a equals 10a. Okay, so what that means is I need to bring this negative 2a over to the right side. So inverse of negative 2a is positive or plus 2a. So I'm going to add 2a to both sides. And I get 40 equals 12a. Still not done. I got my very last and final step, step 5. And this goes over to the next slide here. I have to divide both sides by 12. And I get a equals 10/3. And simply all we did here was 40 over 12. That doesn't go in evenly. So remember I said we don't need to change them to mixed numbers. We don't need to change them to decimals. All we have to do is reduce. So since 40 and 12 are both divisible by 4, that gives us 10/3. Okay? So that's an awesome problem. It's got every single step in it. So, you know, I'm going to skip this problem. Actually, no, you know what? I'm going to do this problem. Anywho, this problem's got everything in it. This might not hurt to watch again. Okay, so now let's go on to this next problem. Don't get freaked out by the fractions. It really doesn't have much of a bearing on it. So let's go ahead and take a look. The first thing I need to do here, I need to distribute this 1/2 to b plus 6. And when I do that, I get 1/2 b plus 3. Because okay, 1/2 times there's an imaginary 1 in front of this b is 1/2. And then 1/2 times 6, what's half of 6? 3. Okay, I'm going to drop everything else down. Everything's beautiful. All right, now, again, I got to get my variables to one side, my constants to the other. So I'm going to start off by subtracting 1/2 b on both sides. The nice thing about this, you don't have to clear out fractions because they have the same denominator. So there's no need, right? So the left side, I'm left with 3. Okay, this gets a little tricky. They kind of skip a step here, but what's 3/2 minus 1/2? 2/2, or 2 over 2, which we know reduces to 1. So this becomes a b. Look how pretty that is. That ends up being super pretty and easy, right? Okay, so now I'm going to do the inverse of minus 1. I'm going to add 1 to both sides, and I get b equals 4. Okay, so that's how you solve equations with variables on both sides. Now, the next thing I'm going to show you is a little different. So you need to know this for not only just solving equations, but the stuff we do in the future in this class. You're going to need to know how to recognize this stuff. So when we have something called an identity, okay, what that means is we have an equation that is true for all values of the variable. And when we have that, we call that infinitely many solutions. Okay, that's when the statement is always true. And I'll show you what that means in a second with some examples. When you have statements that are false, that's a little different. We call that no solution. So sometimes we can't find one solution. We might find all kinds of solutions. Sometimes we can't find a solution at all. We call that no solution. So I'm going to show you. This is in your book, but maybe just kind of watch, but it wouldn't hurt to jot down or at least refer to it in your book. So if you look here, if we're talking about identity, okay, if you have 2 plus 1, that equals 3, guess what? 2 plus 1 equals 3. That's a true statement. Sometimes you may solve an algebra problem and your variables go away for whatever reason and you have just numbers left over. 2 equals 2. That's a true statement. So this is where we would say we have infinitely many solutions. Okay, so if 2 equals 2, we know that to be true. So it has infinitely many solutions. Now, if you have an equation that's false, such as 1 equals 3, or when you go to solve this problem down here, you get 0 equals 3, we know those are false. 0 does not equal 3. It's false. So we would just simply write down no solution. Okay, so let me show you some examples of when you have infinitely many or no solution. Okay, so we have a nice long problem here. 10 minus 5x plus 1 equals 7x plus 11 minus 12x. I'm going to look to distribute. There's nothing to distribute. I'm going to look to combine like terms. And if I look here, I got a 10 and a 1 on the left side. On the right side, I got a 7 and a 12x. So I'm going to combine those like terms, and I can bring it down to 11 minus 5x on the left side, because 10 plus 1 is 11. And then I've got 7 minus 12x, which is minus 5x. So again, on the right side, I have 11 minus 5x. So now, right here, I can actually stop my problem, because 11 minus 5x is always going to be the same as 11 minus 5x, right? We have a true statement already, but I want to kind of show you based on what we did before. So if I try to solve and I add 5x to both sides, looks what these cancel out. These 5x's and these 5x's cancel out. So I'm left with 11 on the left side, 11 on the right side. Is that a true statement? It sure is. So that means we have infinitely many solutions. Or you can even say all real numbers. I like all real numbers a little bit better, but either one is fine. Okay, so if you end up with a problem like this and your x's go away, or if your constants go away and you're left with x equals x, don't freak out. If it's the same thing, it's the same thing. It's a true statement, and we have all real numbers. Okay? Let's take a look at another one here. 12x minus 3 plus x equals 5x minus 4 plus 8x. Again, I'm going to combine like terms. And I get 13x minus 3 equals 13x minus 4. Uh-oh, we have a minus 3 here and a minus 4 here. Mayday, mayday. These are not the same expression, but let me continue to show you. If I subtract 13x on both sides, my x's on both sides cancel out, and I'm left with negative 3 equals negative 4. That is not a true statement. Okay? Nowhere on this planet, or probably on the universe, does negative 3 equal negative 4. So what that means is we have no solution to this problem. Okay, so you would literally write no solution. The previous one, you would write all real numbers or infinitely many solutions. So that's part of the answer that you have to write down. Okay? Yay, so fun. All right, now, before everybody, I know I could hear you from home with the like collective sigh of like, oh no, a word problem. These word problems come up like literally every chapter in this book, and it's just like this type of word problem. Okay, so what I want you to do is just take a deep breath. No biggie. We're going to work on it together. And we're going to take it step by step. So again, just write the keywords for this problem, for the words. John and Sarah are planting tulip bulbs. John planted 60 bulbs and is planting at a rate of 44 bulbs per hour. Okay, so far what we know, John has already planted 60 bulbs. That's our constant. It's not changing. The rate at which he is planting is 45 bulbs per hour. So that's going to be where your variable is. Okay, next part. So real quick though, John is one side of the equal sign. Sarah is going to be the other side. So Sarah has planted 96 bulbs and is planting at a rate of 32 bulbs per hour. Again, 96 are constant. It's already happened. 32 is going to be with our variable. In how many hours will John and Sarah have planted the same, that means equal sign, same number of bulbs? And how many bulbs will that be? So we're taking John's planting ability and setting it equal to Sarah's planting ability. Once we do that, we'll then solve for the variable. Okay, so Actually, let me go back because really the keywords are right here.